Next we have Eric Barton. He's the lead architect for lead architect at the High Performance Data Division at Intel. He's truly the luster fashion plate. My understanding is that people referred to his purple jacket as the luster jacket. He's scrambling right now to get to the microphone for fear that I'll talk some more about him. Oh, the father of Elnet, acrobat, guitar player, singer, roller skater.
Nope.
Hockey player.
Nope.
No, I'm a man that hardly needs an introduction, but I could go on.
Give us a break, eh?
I'm sorry?
Give us a break.
Ladies and gentlemen, Eric Barton.
Hello. So I'm going to talk about my favorite hobby horse, which is I/O at Exascale. Favorite pet project, indeed. So this is, we're in just about in the final quarter of the fast forward storage and I/O project at the moment. We started this a couple of years ago, and really our intention was to change the way I/O was done. I/O is always an afterthought, and I guess it comes from the fact that application developers are just thinking about the science all the time and worrying about how they will, make new discoveries. And unfortunately, their simulations, have to save stuff from time to time. But the real thing is actually doing the simulations. And then I/O people they just regard the applications as a complete black box. We don't care about what's going on in the applications. Who cares about floating point? I worry about bytes moving around the system and hitting disks. And so when you get people with two such very sort of entrenched and non-overlapping viewpoints, then it's no worry. It's no surprise then that I/O is the unloved bastard child of HPC application developers. And we wanted to change that. Because at Exascale, the amount of data we believe, well, apart from some, maybe QCD applications are still only going to say 53 at the end of days of executing. But we think most Exascale applications are going to be working on much, much, much bigger data models. They're going to be simulating the same set of simulations in many, many different ways for uncertainty qualification. And so data really is going to be a big deal. And we wanted to turn data into something people loved, something people could engage with and really understand. Make data, or the I/O subsystems, a tool of the scientist instead of being, some horrible thing that we don't ever want to think about. Now, to do that, there's some serious challenges to overcome. The only way that we're going to get more performance out of exascale computers is by increasing the parallelism. So we can't make the processors run any faster. In fact, the faster you clock them, the more energy inefficient they become. And so the trend is in the reverse direction, to clock the processors more slowly. And so you need many, 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 many more processors than we're used to today. And that's a problem for I/O, because Amdahl's law is always there. Scratch the surface and you'll find Amdahl's law. Why? Well, it's when any individual stream of I/O kind of pokes its head above the parapet, That's the new ceiling. So although all of the rest of the I/O in the system, maybe hundreds of thousands, maybe millions of streams, they might all have plenty of headroom to get through the particular nooks and crannies of the fabric that we're pushing them through. But this one stream here is limited, which means that now the effect of that one stream is now magnified 100,000-fold over all of the rest of your streams, and your utilization just plummets. So in order to produce a scalable I/O system, we have to find ways around of eliminating or at least ameliorating these sources of Amdahl's law. And so one of the ways of doing that is to go full scale for asynchronous interfaces, so that we reduce our dependence a lot on blocking I/O, and we can get a lot more overlap. Applications developers know all about this, and communications for computation have had to overlap compute with communications, and it's just the same for I/O. The other issue, though, when you have a huge data set, is, how am I going to manipulate it? Now, today, I think we abuse the file system namespace. So, file per process is a common way of using file systems, in which every single process creates its own little file. It's got some great properties. Because we've told the file system up front that these are independent units of I/O, it's not going to get in our way. That's the problem with shared file, which PLFS was created to address. When I do shared file so that I've got a single name for all of my data, I've lost my way of specifying, at least to POSIX, that these different parts of my data that I'm sharing inside this, that I'm placing inside this shared file, are really non-contending. And so the system, which is trying to do the right thing, ends up contending with itself in order to implement the difficult case, which the application actually isn't even exercising, of contending data. And then you end up with unnecessary locking, and there you go. So we intended to adopt asynchronous interfaces and get away from the whole concept of locking to implement this I/O system. The third issue, which we don't really address today, is also has to be addressed as a result of the increasing size of these data sets. So if I have spent all of my life painting the Mona Lisa, when I go to put my final brush stroke on the Mona Lisa, I don't want to smudge it and write off a whole lifetime's worth of work. Okay, what does that mean? In actual fact, for a data set, it means if I have to throw away my data set because the application screwed up just as it was completing the final output to the data set, I've lost a whole bunch of work. And so what do you end up doing? Again, abusing the file system namespace and putting all of your incremental changes to your data into separate named files. So you end up with this completely unmanageable namespace, because the namespace has stopped doing what it's there for, which is helping you find your stuff, and you're using it to help you make your application resilient and scalable. So those are the things we wanted to get away from. Now, what context are we going to be using this I/O system? Well, our original thoughts in the Fast Forward project were in this sort of workflow situation. We have a scientist sitting at his workstation. He's connected to a site-wide storage cluster where the majority of his data is going to be. That's where all the capacity storage is. There is an Exascale cluster where simulations are going to run. And there's a burst buffer on the edge of the cluster which is going to do the impedance matching between the bursts of I/O that applications running on the cluster want, with the streaming I/O that the centralized storage system can manage. So the scientist starts off by initiating a workflow session. Now, here, a workflow session means a unit of allocation of machine resources where you can run parallel jobs. So let's say we're going to have a simulation, the blue nodes, it's going to run on the blue nodes, and an analysis program which is going to run on the green nodes. What does the data flow actually look like? Well, before the whole workflow runs, we very painfully and slowly dribble the data from the global file system, well, at a terabyte a second or so, say, into my burst buffer. Once it's there, hopefully in a distribution which matches the distribution that the application wants it in, and so we'd like to be able to specify that somehow. Once it's there, then the simulation can actually start running, pull the data in from the burst buffer, and start computing on it. Whoops. I pressed the wrong button, that's what. Ah, here we go. See, it's very slow to pull it in from the global file system. But then the simulation starts running, pulls it in, computes on it, produces a result, which is then pushed back about 10 times faster than you can do I/O operations to the central storage, back into the burst buffer. Now that it's in the burst buffer, the analysis application can get at it. Now, again, both the simulation and the analysis program have got good cross-sectional bandwidth into the burst buffer. The analysis program might even want to corner turn the data because the transpose that it's doing the analysis it's doing might be column major, whereas the simulation generated the data in row major order or whatever. So we might have to do a reorganization there. And then slowly, we can dribble the data back to the global file system. So that's one of the major use cases, and DOE procurements like Trinity and Coral are actually predicting this as one of the major ways that these machines are going to be used, and asking people to bid for burst buffers as a result. Now, once the data's in the global file system, I'm going to want to actually browse it. How do I know that my simulation output was right? I mean, I did some analysis on it. I can look at the results of that, but maybe I'd just like to go and look at some point samples of it. So on my workstation, I've got the same data set mounted, and I can go and look at it. The problem is that looking at it, I've only got this piece of wet string between me at the workstation and the file system. I can only look at it through this tiny, tiny keyhole. So if I want to do anything big on the data, I either need an index, which makes the data searchable, or I need to find some way, I could ship it, I guess, back into the compute cluster and run my analysis there. But maybe I could run my analysis right where the data is itself. So instead, I can send my query off to the storage. The storage can then spool through all of the data in parallel, and then my query can be returned back to the workstation. So a mode of operation called analysis shipping. So when you look at these different ways of using the file system, it's very tempting to come up with the idea that, well, actually, the file system needs to be able to run application plugins all over the place. The problem with that is that you're doing resource sharing and running unpredictable application code all over the place. And wouldn't it be better, really, if we could run these plugins, just like normal applications? And I mean, we do have safer environments for running applications, things like Linux C groups, for example. So if we could configure our stack, our I/O stack, to run in all of these different places, I could just run them in sandboxed environments, just like normal applications. And now I've got all of this flexibility. So we came up with a stack in which we separated some of the functionality in different layers of the stack and configured the stack so that it could be run in different places. So up at the top, the idea is that we could produce a stack that had many different top layers that varied depending on the application area, and a single bottom layer which did the common sort of I/O. Down at the bottom layer, throughout the stack actually, we need to have asynchronous and transactional APIs so that we could engage cleanly with failing hardware and software. But down at the bottom layer, and throughout the stack, we'd also want to have APIs that could give you information about the topology. Where is my data in the layers below me? How far away from me is this part of my data? But then at the bottom of the stack, those queries would give you information that were very strongly informative about the personality of the storage that you're working on. And then at the top of the stack, applications would be very free to interact with the stack using the idioms of the application themselves. So we've got user objects, application objects right up at the top of the stack, and these could have enormous dynamic range. We could have a single array, for example, that's a petabyte. Or we might have, 1 billion scalar entities. Down at the bottom of the stack, though, we know we're dealing with storage. And so in the case of disk-based storage, we're probably dealing with thousands, tens of thousands of streaming storage devices. And really, what we want is something in the middle that can understand the personality of the underlying storage and implement these application objects with their vast range of size and distribution and behavior efficiently on top of those bottom layers. And that's where this middle layer, the I/O dispatcher, comes in. It's the reshuffler. It's the thing that understands the underlying storage from a performance and a functionality point of view, and understands, in gross terms, application objects, and squares the circle. And then connecting these layers of the stack, when the stack layers are co-located, then we just want to call straight through. But if we have to run different parts of the stack on different places, then we need something that's an efficient RPC transport, something that's normally thought of as function shipping. So here we have it. Here we have, for the original use cases we envisage in Fast Forward, these are the various ways that we want to be able to configure our I/O stack. So on the left, we have the compute nodes. That's where the actual simulation's running, maybe analysis as well. And it's got a high-level object API, and the one that we prototyped in Fast Forward is HDF5. Connecting HDF5 to the next layer down, IOD, is an I/O forwarding client connected over the fabric natively to an I/O forwarding server. And now there on the burst buffer, being able to manage that storage sensibly is the middle layer that's doing the impedance mismatch. Down at the bottom, on the storage servers, that's where the lowest level, the DAOS layer, distributed application object storage server, is running. So the path from the compute node through the I/O node to the storage servers, that's one stack instantiation. But also, if we're doing analysis shipping on the servers themselves, another stack instantiation will have the whole stack there on the storage servers. And yet another instantiation of the stack will have the top 2 layers running on the scientist's workstation and the bottom layer running on the storage server. Now there's a game changer over the horizon. Which is NVRAM. Load, store, granular memory that doesn't forget is really going to change the way we have to think about computation. And the reason is really, the clue is in that bottom table. If I think of one of these large Grand Challenge HPC clusters, if I think of a working set on the order of, petabyte, say, it's going to take me about an hour to move one working set in or out of a disk-based storage system. With a burst buffer on the edge of my cluster, I've got a small amount of high-performance storage, good cross-sectional bandwidth from the HPC fabric into it, and there I can reduce that by an order of magnitude down to 6 minutes. But with NVRAM on every node in my cluster, I get another almost 2 more orders of magnitude improvement in performance. And actually I can do a brute force search of all of my data in 6 seconds. The number of data sets that I can afford to store on my global file system, is tens of working sets. In my burst buffer on the edge of the system, they're typically being spec'd at 3 to 5 working sets. But a machine configured with considerable quantities of NVRAM could once again get you back to an order of magnitude, or 10 to 30 odd working sets. Now, if my data is right there in the machine, I can do a lot more with it. I mean, for a start, I could stop thinking about it as files. I could start thinking about it as distributed persistent memory. So that, in fact, I can eliminate I/O entirely. I just, I map this NVRAM, I work on it. The next phase of the workflow comes along, just maps it into its memory, works on it, and that way you can stage through a whole bunch of different applications through a workflow, and the data didn't have to move anywhere. You can also start thinking about an order of magnitude larger weak scaling. You can increase the problem size and start doing out-of-core style problems, because the DRAM costs today would just be prohibitive. So what do the workflows look like in this situation? Well, let's say I've got a few workflows already working in my cluster, and I'm about to schedule workflow number 4. It wants to work on a persistent memory image, distributed persistent memory image. The last time I ran it was over there. So we'd probably better migrate it over to where the program can be spawned right now, because I need direct load store access to every segment of my distributed persistent memory image. When you think of it, though, probably what I have to do is actually make some space for it once it's there. Or before it gets there. And so really what I probably need to do is actually evict the data that's there. And where did I evict it to? Well, where I just pulled the data from. So in fact, a more reasonable scenario might be something like this, where after a few iterations, my data from the last time I ran got scattered throughout the machine. And now I'm gathering it all together at the start of my workflow. Probably, this isn't going to be very often. If I get, 3 hours of runtime on this cluster, this reorganization has to happen once at the start. So it's a relatively small cost. And it's going to be complete in seconds. That's a much different situation from the one today where we're imagining we have to start staging data from centralized site-wide storage at like an hour before I'm actually going to need it. So there are some differences between persistent memory and storage, much as they sound like the same thing. Actually, persistent memory is local to the processes using it. Yeah, you can implement a PGAS for non-local access on top of it, but fundamentally, you have to engage with the personality of the storage, which is the storage has the memory has great affinity for particular ranks of my application. Another issue which programmers are going to have to take on board is I can't just abandon my persistent memory image if the machine crashes. If a node crashes, for example, how do I continue? I mean, I can eliminate the need for, or apparently eliminate the need for crash dumps, but I need to be able to continue from where I last left off, even if where I last left off was unexpected. So I'm going to need some way of converting from something that's persistent memory, which is local to processes and fast, but becomes inaccessible when nodes fail, to something that's going to be globally accessible, is going to be consistent and durable so that I can survive node failures, I can pick up from where I left off, and also do the normal sorts of data management on it. So new APIs are going to be required to provide applications programmers with persistent memory as a new programming method. So one of the things that we're thinking about now is how can we make the fast-forward stack that I described previously work in this new situation? Well, one of the things that becomes clear is that software that's been based on conventional networking and conventional disks has had, milliseconds of latency that it can, that because it overlaps data movement and pipelines data movement, there's a much more, it can exploit the relaxed latency. So when I go and read from a disk, it's going to take me probably tens of microseconds by the time I've executed a conventional network stack. Add that disk head seek latency, milliseconds now. And so the fact that my ext4 file system added maybe another few tens of microseconds of latency to that is really in the noise. But if I'm trying to exploit NVRAM latency, which could be sub-microsecond, with an integrated fabric, which could have round-trip latency also on the order of a microsecond, I've really got to think again about my software that turns raw NVRAM into a storage system. And so the thing that we're thinking about is, well, I can't afford to be doing system calls. I've got to have OS bypass end-to-end in order to not incur the additional latency. I've got to do my security negotiation once off and establish a communications and security context that lets me get at my data. And this security context has got to be scalable and many-to-many. If I'm thinking of scaling to, say, 100,000 clients, I can't afford to be keeping connection state on each of my clients. So we've got a model for a versioning object storage device. The lowest level of the fast-forward stack, DEOS, uses a multi-version concurrency control method, and we want to extend that to NVRAM. It will be programmed using a persistent memory programming model. It will be implementing fine-grained transactions so that upper layers don't have to. And it will, on writes, it has to integrate these writes into the versioning, effectively logged writes, which are, it turns I/O into being completely commutative. So it doesn't really matter the order in which I/O comes across the network at the server. It's integrated in the order that the application needs it to be integrated. And it's also undoable, so that when incomplete transactions occur, transactions that can't be completed, all of the I/Os associated with them can be removed in time corresponding scaling with the size of the transaction rather than the size of the data set affected. Now this stack, again, will have to be configurable. We'll want it to run in different places. And here we see how that affects the layout of the stack as we implement the API. We provide the same API functionality, but underneath it, two quite radically different implementations. One that's tuned for the in-memory version, and the other one that's tuned for disk. So, a quick summary. I think that new architectures, new cluster architectures with NVRAM on many compute nodes really does change the game. Approximately 3 orders of magnitude. It isn't something you can ignore. It's going to change programming models, and it's going to change HPC workflows. Any questions?
Eric, so back on the previous slide, sorry, back up one more.
This one, oh, that one?
So the question, you made a statement that the local node was going to do, for the versioning OSD, the local node was going to do its own transaction coalescing there? Was that on a per node basis?
The way versioning object storage, the way multi-version concurrency control works is basically the storage just remembers everything and how it should and how it should be, all the writes. Start again. It remembers how all the writes should be applied in transaction order, whether they arrive out of order or not.
But that's on a single node.
That's on a single node. And so an application which is doing which has a vast number of processes, doing a transaction against a vast number of storage devices, the threads all doing the parts of the transaction have to agree on the version number that their transaction, or the transaction number that their transaction forms a part of.
I see. So there's 2 layers of transactionality then, one on the node and one
No, not at all.
through the
well,
application.
yes. So there are 2 aspects to it. Yes, there's the integrating writes and remembering the transaction order in which the writes should apply, and then there's giving transaction numbers to the application. I mean, this is a well understood technique actually that the Oracle database itself actually uses. It means the major benefit of it is that readers always see an immutable version of the past. Writers all write to some future. Now, if the writers don't manage to complete a write, that write stays in the future forever. You never see it.
I have a second question. if you're doing the storage locally on the individual node for the memory OSD, there's no access to that data if that node dies.
Indeed.
Right? So as we're talking exascale levels, they're going to have a large number of node deaths.
Yeah.
So are we going to be undoing constantly?
When nodes die, you're going to have to abort the transactions that affected those nodes. Also, your transactions should be replicated sufficiently so that the data does survive node death. Now, if you're replicating if you're replicating enough, your write transaction could potentially survive the failure of any individual.
So this is kind of the Hadoop model of processing.
Well, it's generalized actually in Paxos. You can use Paxos as a way by varying the proportion of nodes that have to be in a read or a write quorum. You can actually for any particular subset, then you can be insensitive to more or fewer nodes.
But fundamentally, you're paying an overhead price, basically, of doing extra computation and extra storage in order to make up for that resiliency.
No, I don't think so. You're inserting your data into an index in order to ensure that when you retrieve the data, what you're retrieving is the data as if it had been written in the correct order. So there's some overhead for that. And probably what you'd want to do is some sort of aggregation. Existing programs like Cassandra, for example, do exactly that, or Bigtable. So you write deltas, you integrate with the lowest latency you can so that reads can occur quickly. But then over time you can make that integration more efficient and to save space and save latency on lookups.
Eric, this one? Yeah. Remind me again, what are the deliverables you have to deliver for the end of the fast forward? Are there breadboards or models or what is it?
Oh, right. So in fast forward, what we're showing is the first picture. So we're not actually, oops. This one, yeah. We're delivering all the components to implement that workflow. So we're demonstrating burst buffer, analysis shipping, transactional, complete top-to-bottom stack, asynchronous interfaces, and data reorganization. Yes.
Do you have any performance numbers of what you're achieving in the fast forward project? Trying to get a feel for what direction we are headed.
Yes, we don't have performance numbers that we can share yet.
Starting to finish first.
Yes. Oh, speak to Soren about performance, please.
We're doing our best to show very good performance.
Okay, that's all we got time
Right.
for. Thank you, Eric Martin.